Imagine walking through a forest where every tree tells a story, not just of nature, but of mathematics. Welcome to Understanding Weighted Averages in Shannon Diversity, a journey that bridges simple averages with the science of biodiversity and information theory. Guided by M.W. LaSalle, we'll explore how basic math transforms into powerful tools for measuring the richness and complexity of life. Let's embark on this exploration where numbers illuminate the hidden patterns in our natural world. Let's start with a classroom puzzle. If 8 students score 90 and 2 score 50, what's the average? Using a simple average, we just add these two numbers and divide by 2, getting 70. But is that really fair when most scored higher? Weighted averages come to the rescue. By factoring in how often each score appears, the frequency, we find a more accurate result. The sum of 8 multiplied by 90 and 2 multiplied by 50 is 820. Dividing that by 10, 82. This shift from equal treatment to weighted fairness lays the groundwork for understanding complex systems beyond the classroom. Building on that idea, let's uncover how expected value emerges. First, we count frequencies, tracking how often each outcome occurs, like tallying coin flips. Then we calculate a weighted average, giving more influence to frequent results. As our dataset grows, these frequencies become probabilities, revealing deeper patterns. The expected value, the heart of probability, blends all possible outcomes, each weighted by its likelihood. This concept is essential for predicting trends, whether in games of chance or in understanding nature. Take your time and read the slide. Let's put expected value into action. Picture a bag with 7 red marbles worth 2 points each and 3 blue marbles worth 5 points. What's your average score if you pick one at random? By multiplying each marble's point value by its probability, red at 70%, blue at 30, we find an expected score of 2.9. This simple calculation shows how probability and value come together, offering insight that goes far beyond guessing. Now let's tackle the biodiversity challenge. How do we measure the true diversity of a forest? Counting species alone falls short. We must consider richness, how many species there are, evenness, how balanced their populations are, and abundance, the frequency of each species. Imagine the difference between 100 trees of a single kind versus 10 trees each from 10 distinct species. Real diversity isn't just about numbers. It's about balance and variety working together. Bringing it all together, we see how averages, assigned values, like those for the marbles, and now species values connect. In ecology, we use ln/pi, the natural log of a species proportion, to represent its value. In this case, the expected value is called Shannon Diversity Index because of the unique way the value is calculated. This formula builds on everything we've learned: probability, expected value, and meaningful measurement. It's a powerful example of how simple math concepts evolve into tools for understanding the breathtaking complexity of life on Earth. Let's unravel how the Shannon Diversity Index comes together, step by step. First, each species gets in value, calculated as minus the natural log of its proportion in the ecosystem. This negative sign flips the value positive, since low values have negative logs. Next, we weight each species by abundance, so common species, though less surprising, still shape the index. Remember, it is very similar to the expected value. We assign a value to each species and multiply by its relative abundance. Consider the marble example. Finally, we sum these weighted values across all species. The result? The Shannon Index, a single number capturing both the richness and evenness of life in an ecosystem. It tells us how uncertain we'd be when guessing which species a randomly chosen organism belongs to, a direct link between mathematical formulas and real biodiversity. Imagine a forest with oaks, pines, maples, and birches, 100 trees in all. Each tree species' relative abundance, or PI, and its value on PI are tallied up. Even though oaks are most common, pine trees actually contribute more to diversity because their relative rarity means each pine offers more information. Information represents what we learn about the ecosystem's uniqueness. When we encounter a surprising outcome like a rare species, the information value is high because we gain significant new knowledge. The rarer the species, the more surprised we are to find it, and thus, the higher its informational value, to our understanding of the ecosystem. Birches are the rarest, so they're the biggest surprise when found. Yet their low numbers keep their overall impact small. The Shannon Index sums these surprises, revealing that diversity is shaped by both abundance and rarity. It's not just who's there, it's how unexpectedly you encounter them. Rare, or common, which matters more for biodiversity. Rare species, like a single unique tree hidden among mossy roots, bring exceptional value by offering unique habitats. Yet because they're so scarce, their total impact is limited. Only a few other species can depend on such limited resources. Common species may seem less exciting, but form the backbone of the ecosystem's stability. Think of a golden forest filled with familiar trees. The Shannon Index beautifully balances this ecological paradox. Rare species pack a punch per individual, but common ones dominate the big picture. This blend of uniqueness and abundance defines true ecosystem diversity. What's so surprising about spotting a robin versus an eagle? Seeing a robin is expected, there's no new knowledge gained. But catching a glimpse of a rare eagle soaring overhead delivers a jolt of information. In math terms, surprise is measured as LNPI. Certainty brings zero surprise, while improbability sends surprise sky high. Each rare encounter rewrites what we know about an ecosystem. The less likely the event, the more it teaches us. A beautiful connection between ecology and information theory that lies at the heart of the Shannon Index. The Shannon Diversity Index transforms ecosystem complexity into measurable information. In a vibrant woodland, every new observation could reveal something unexpected, because greater diversity means greater uncertainty. Mathematically, encountering a rare species brings high surprise. Meeting a common one confirms what you expect. The formula for H averages these surprises across all species, much like expected value and probability. Both concepts use weighted averages to connect statistics with nature's unpredictability, illustrating how simple math evolves into profound ecological insight. How do we measure ecosystem health in a single number? The Shannon Diversity Index does it by quantifying the average surprise of meeting each species. It multiplies each species' proportion by its information content and adds up these values. H equals minus pi times ln pi. When all species are equally common, H reaches its peak, reflecting maximum diversity and balance. If only one species dominates, H drops to zero, a monoculture with little resilience. This index turns complex communities into clear indicators of ecological richness. At its core, the Shannon Diversity Index asks, how surprised would you be if you randomly picked a member of this community? High diversity means you can't easily predict what you'll find next. Each encounter brings fresh information and insight into the ecosystem's structure. This index elegantly blends richness and evenness into one measure, revealing not just how many species exist, but how evenly they share their world. As unpredictability rises, so does our understanding and our appreciation of nature's true complexity.